Our Metamorphic Rock Lab has a couple of errors when it comes to the heading at the top of the page. This one should say Lab 20 at the top. It says Lab 19 for a couple pages, and then it even jumps and says Lab 7 at some point. So don't be confused. This is Lab 20. If you have a PCC rock kit, you should have these 7 rocks. They are in their own baggie, and they begin with the lowercase letter M. We're only going to be using 5 of these in the lab identification part of the lab. 2 of these are just a little bit tricky, but I'll still tell you what they are. Number 4 is what's called a talc schist or a soapstone. Now, talc is a mineral, and it's actually the mineral that's in baby powder, and it's a metamorphic mineral, and this is a talc schist, which is a metamorphic rock made of that particular mineral, sometimes called a soapstone. And if you're familiar with the current controversy over asbestos being in baby powder, well, asbestos is another metamorphic mineral that often occurs with talc in metamorphic rocks. And so it's an actual mineralogical problem that talc and asbestos occur together. And in some cases they occur together and they're hard to separate. So that's a little side note about talc and baby powder. The other rock we're not going to use is this M25, and the reason I don't want to use it is because, first of all, I don't think we even have a video for M25, and second of all, it's called an actinolite schist, and it really is pretty much mostly actinolite. Actinolite's a mineral. It's a metamorphic mineral that you looked at in the last lab when we looked at metamorphic minerals. And this particular rock, at least the sample I have, is just about 100% actinolite. I don't see any other minerals in there. So calling it a rock, to me, is like calling a quartz crystal a quartz rock. It just didn't make sense to me. So we're going to use the other ones, but we'll also add these from the videos as well. The pre and post lab questions are pretty short this time. We just have 2 pre-lab questions and 4 post-lab questions. In fact, they're on the same page. I've just kind of blown them up. And then we get to our metamorphic rock identification chart. This one again says Lab 7 at the heading. It should be Lab 20. So just like most of our other rock classification schemes, we're going to look at texture and composition. Texture in this case is going to be divided into foliated textures and non-foliated textures. And remember, foliated means that the mafic and felsic minerals have been separated and form linear patterns. And we can go from a fine grain pattern of foliation, in which case, because the mineral grains are so fine, we really can't even see the alignment of the minerals, except that we can see that there's a slaty type of cleavage or a very flat type of orientation of the minerals, and slate and phyllite are examples of that. When we get to a medium or coarse-grained type of foliation, we get into rocks that are known as schists. As we get to an even coarser grain type of foliation, we get into something called a gneiss. Here we usually have very distinct alterations of felsic and mafic bands. If we get as far up into a myelinite, then we get to maybe even smeared layers where melting was almost about to occur. Non-foliated rocks, which are also called granoblastic, are those rocks that do not foliate for one reason or another. And I mentioned in the metamorphic mineral lab that in some cases rocks don't acquire foliation because their mineralogy is just too simple and there are no new minerals that grow. Composition across the top here is divided into the following: aluminous compositions, which have aluminum-bearing minerals; calcareous compositions, which are dominated by calcite; mafic compositions dominated by mafic minerals; quartzo-feldspathic dominated by felsic minerals; and then organic. Along the bottom we have the possible protoliths. Proto means before and lith means rock. So these are the parent rocks. And you'll notice that there's a 1-to-1 correlation between the protolith and the composition. So claystones and shales are going to give us aluminous types of rocks. Limestones are going to give us calcareous rocks, and that shouldn't be surprising because limestone is made of calcite. Basalts and gabbros, which are mafic, are going to give us mafic rocks, and andesites are intermediate. They also fall into that category. Granites, diorites, sandstones, which are all felsic, well, diorite's intermediate, but we're going to put it over here, give us quartzo-feldspathic rocks. And then coal will give us anthracite coal. It's just a higher grade of coal. So I'm going to indicate some of the more common metamorphic rocks. Under the aluminous category, this whole series is quite common. We usually get slate, which can turn into a phyllite at a higher metamorphic grade. It could go then to a schist, or a gneiss, or even a myelinite. This indicates increasing metamorphic grade as you go down the column. For the calcareous group, we tend to have marbles, which come from limestone, and because their chemical composition is so simple, we don't have a whole lot of different minerals in them. We just have calcite, unlike aluminous minerals where we can get chlorite and garnet and sillimanite and staurolite and all kinds of other minerals. If you missed my metamorphic mineral lecture that went along with the lab, you should definitely go back and look at that. In terms of the mafic metamorphic rocks, the one that we're going to focus on here is serpentinite, and that comes from metamorphosed basalt or gabbro. And these are common in California because serpentinites are common in California. Quartzo-feldspathic metamorphic rocks that are common are quartzite, and that comes from metamorphosing sandstone, another thing I talked about in the metamorphic mineral lab. Finally, anthracite coal is from metamorphosing bituminous coal, and that's the only organic example we have here. One thing to remember is that serpentinite is California's state rock. So what do we have in lab? Well, you're going to be looking at 11 rocks, and these are the ones to choose from and the number of each that you have. But we are going to look at some of these. So let's start by looking at number 3. I put number 1 here just to leave a spot, but I want to start with number 3. As usual, you're going to go and look at the videos. I don't think I need to show you where they are anymore. And what we can see with mineral number 3 is that there's definitely a foliation in here. We have bands of dark and lighter colored minerals. And the lighter colored minerals are a distinct pink or salmon color, indicating that these are probably pink potassium feldspar minerals. And the dark ones are undoubtedly mafic minerals. So this is clearly foliation, and it's a very coarse foliation. The minerals are big. We can clearly see the difference between mafic and felsic minerals. So we're going to say that this rock is foliated, and we're going to go with coarse. So somewhere in this row. And then, because I saw potassium feldspar, I'm going to go with this column. Now, I told you that we're probably going to have mostly aluminous rocks here, so I'm kind of giving you an exception to the rule here, but don't worry about that. So where these two meet, we find a gneiss. And if you had found the gneiss over here, that would have been fine. So filling out the chart, we're going to say that it's a foliated rock with coarse foliation. The mineral composition has pink feldspar and dark minerals. And just do your best to describe the minerals. The possible origin in this case is a granite. Let me jump back to why I said that. Because I chose this column, I'm going to say that this might have been a granite because granites commonly have these big pink feldspars in them. And I'm going to name it a gneiss. Let's try M13. Here's a picture of M13 during the video, and what you can see is it's extremely fine-grained. I don't see any crystals at all. It's kind of shiny. It's got a very flat surface. As the person turns it, you can see that there's a very sharp edge and these very, very flat surfaces here. These are actually called rock cleavage. They're so flat. We look at the other side and we can see layers, very, very fine layers. So this is foliation, but we don't see any minerals. So this is what we call very fine foliation. So we're going to say fine-grained foliation. So we're going to be somewhere in this part of the chart. Now you'll notice that here, these particular types of rocks are rarely observed. So we're going to cross out calcareous. Same with over here. These are rarely observed. So we're going to cross out this. And there's nothing inorganic, so we're not going to look there. Now in the mafic column, this would represent a rock that's either a green schist, a hornblende schist, a blue schist, or an amphibolite. And all of these would have large enough crystals to see and would have a whole host of minerals such as these that we don't see in the rock. I know this is advanced. You're not seeing what I'm seeing, but you have to trust me on this. So we're not going to choose that. We're going to choose the aluminous column. And in this case, we're going to choose slate. It's a very fine-grained rock with what I call rock cleavage. And it probably came from a shale. So we're going to say it's foliated, it's fine-grained. I'm going to select aluminous for its mineral composition. It's probably from a shale, and I'm going to call it a slate. Remember, this is brand new for you. I know we haven't had a lot of time to look at metamorphic rocks and minerals, but do your best. Of the 11 samples you have, you only have 9 more to figure out because I've done a slate and I've done a gneiss. So do your best watching the videos, trying to figure out what you have. Use the process of illumination. Use your hand lens with the samples that you have if you have samples at home. And do your best to try to figure out which metamorphic rocks we have. Good luck.